Totinos, how did you know? Totinos, Totinos, everybody's talking about Totinos, Totinos, hot pizza rolls and not burritos.
So let me start by saying we're going to assume that R is a commutative ring with identity. My primary reference for this material will be notes by Keith Conrad on tensor products. I find the presentation to be quite a lot simpler to understand than the presentation in Dummit and Foote. And I think the biggest reason why is that Dummit and Foote go to pretty great lengths not to assume that R is a commutative ring from the start. So there are situations where it's important to understand tensor products where the ring R is not commutative. But I think that it's helpful to first really well understand the case where R is commutative. And then later on, when you need these applications where R is non-commutative, you can go back and think about this more general picture. All right. So I'm not going to tell you what a tensor product is in this video. We'll talk about that in the next lecture. But I want to get us started. So let's say M and N are R modules. We want to define something which we're going to call a tensor product, which will be another R module, M tensor N. So this symbol here is O times in LaTeX, and you put the little subscript R to indicate that you're taking the tensor product of two R modules and getting out an R module. So it's important to have this here sometimes because you might have the same set M can be an R module for many different rings R. So this really emphasizes like what exactly it is that you're considering. So rather than define a tensor product, what I want to do is tell you a major important property that tensor products have. So let's say P is any R module. The key thing about tensor products will be that R module homomorphisms, which it'll be helpful for us to call them R linear maps going forward, phi from this tensor product, M tensor N, to this R module P, will correspond to bilinear maps from the set M cross N to this R module P. So one way to understand what a tensor product is that linear maps out of a tensor product to somewhere correspond to bilinear maps from your direct product to that same R module. All right, so in order to understand why this is such an important property, we're going to talk about bilinear maps. All right, so here I'll give you the definition. A function B from the direct product M cross N to P, where M, N, and P are R modules, is called bilinear if it's R linear in each argument when the other argument is fixed. So what does that mean concretely? B of M1 plus M2, comma N, has to be B M1N plus B M2N, where this addition over here is taking place in this R module P. Okay, so you're holding N fixed. You see that you have a kind of distributive law for addition in the first argument. Same thing if you keep M fixed, you have this distributive law in the second argument. B of M plus N1, N2, sorry, B of M, comma, N1 plus N2 is B M N1 plus B M N2. So you have a similar distributive law in the second argument with respect to addition. Well, what about the action of R on M and the action of R on N? B of R times M, comma, N is R times B of M, comma, N. Similar, B of M, comma, R times N is R times B of M, comma, N. So you can pull out these R's if they occur in either of your two arguments. So what we're really seeing here is that if you pick some N in the R module N and keep it fixed, and then you see what happens is you vary the thing in the first coordinate, B of something comma N that is an R module homomorphism from M to P for any fixed n in your R module n. So for each n, you're getting some R linear map from M to P. And same thing, if you fix little m, and then you let the thing in the second argument vary, b of m comma something, gives an R linear map or an R module homomorphism from n to this R module P for any m in your first R module. All right, so these maps have a lot of structure. And in order to understand this bilinear condition, I think the most helpful thing to do is to look at some examples and then also at some non-examples. So I'll pause and erase, and we'll spend the rest of this lecture talking about examples and non-examples of bilinear maps. Let's give some examples of bilinear maps. One thing I like about the presentation in Conrad's notes is that it builds on some things from linear algebra that you already know well. So one example of bilinear maps is the dot product of two vectors in Rn. So dot is a function that from Rn cross Rn to R, and it's bilinear. So first, just to check, R to the n is an R module, where R really is the ring of real numbers, because we know how to scale a vector by a scalar. We have a scalar multiplication of R, the real numbers, on R to the n. Or said another way, I mean, R is a field. This is just a vector space over our field. More generally, you could take an n by n matrix A. I'll use this notation MNR to mean an n by n matrix with entries in R. And we could define a bracket V bracket W to be V dot product A times W. This is a bilinear map. It takes in two vectors, V and W, and outputs a scalar in R. Matrix multiplication gives another example. So we take in an m by n matrix with entries in R, and also an n by p matrix with entries in R. And if you multiply them, what do you get? You get an m by p matrix with entries in R. So the pair AB goes to the product of those matrices, A times B. You can check that this really is a bilinear map. First, also, the space of m by n matrices with entries in R, that is an R module, because we know what it means to take a matrix and scale it by a real number. We have a scalar multiplication of the real numbers on this set of matrices. So you can check that this really is bilinear using what you know about matrix multiplication. And the dot product that we already saw is a special case of this, where this first m is 1, that you're taking a row vector with n entries, and this p is also 1. So this is a column vector with n entries, and you just have to be a little careful where V times W, that is the dot product of V and W transpose. Okay, the determinant is a function that takes a 2 by 2 matrix to a real number. Well, this is just a function of one thing, right? This 2 by 2, this R module that is 2 by 2 matrices. So it can't really be a bilinear function unless you think of the inputs as being each column separately. So this is a bilinear function of the matrix columns. It takes in a vector in R2 and another vector in R2 and outputs a real number. And you can check that first, I mean, each one of these R2s is an R module. And this determinant function, using what you know from linear algebra, you can check that it really is bilinear. All right, so now let's move away a little bit from linear algebra over the real numbers to the setting of a general R module M. What does it mean for M to be an R module? There's a scalar multiplication of R on M. And that scalar multiplication is bilinear. So we have this scalar multiplication that takes something in R and something in M and outputs something in M. takes the pair r comma m to r times m. And this is bilinear. This is like almost the definition of what it means for m to be an R module with this scalar multiplication. If you have a ring, you can multiply in the ring, and that multiplication in the ring is bilinear. So if you just check the ring axioms, you'll see why this is true. So the last example I want to give is a little bit different. If you have a bilinear map from m cross n to some R module P, and then you have an R module homomorphism from P to some other R module Q, then you can compose them because the codomain over here is the same as the domain over here. And the composite from m cross n to Q, L following B, that is bilinear. And this is one where you really should check this once. You should use the fact that you know L is an R module homomorphism and B is bilinear to check that this composite satisfies all the axioms that you need in order to be a bilinear function. So I'll pause and erase, and then we'll talk about some examples of functions from m cross n that are not bilinear, and also just some few last things. I would like to give two quick examples of functions that do not give bilinear maps. So let's say that m is an R module. We can add pairs of elements of m. So that gives a function plus from m cross m to m, where we take m and m prime, and we output m plus m prime. And this is not usually bilinear. Why not? Well, one of the things that this bilinear condition requires is that you satisfy a kind of distributive property in each of the arguments with respect to addition. So we need m1 plus m2 plus m prime to be equal to m1 plus m prime plus m2 plus m prime. And generally, these are not equal. I mean, these shouldn't be equal. You could get unlucky if you do something like take m prime equals 0. But if you don't, you'll see that this is almost never true. All right. The space of n by n matrices with complex entries is a C module. So you can scale a complex matrix by complex number. And you can take this function that takes a pair of these n by n complex matrices, A and B, and outputs A times B conjugate, where you take the complex conjugate of every entry in B before you multiply. And this function is not bilinear. Why not? It is biadditive, meaning that it satisfies the distributive laws that you need with respect to addition in either of the two arguments. But it doesn't behave well with respect to the R module, sorry, the action of the ring R, the ring C in this case, on the second argument. So if you take a complex number Z and you take the pair A comma Z times B, what do you get? You get the matrix A times the matrix ZB or conjugate. And what is that equal to? Well, when you multiply by this scalar and take the conjugate, it's the same as scaling B conjugate by Z conjugate. So what you get, you can just pull that out and see that this is Z bar times A B conjugate, which is not the same thing as Z times A B conjugate, unless Z happens to be equal to its conjugate if it's a real number. So you have to be a little careful where there are some reasonable looking maps that are not bilinear, because you really need to check that you satisfy these distributive properties with respect to addition, these biadditive properties, and also that your function behaves nicely with respect to the action of your ring on each of the two R modules that you have. So I'll pause and erase, and then I'll talk about a few last issues that will set us up nicely to define tensor products at the start of the next lecture. I want to end this lecture by addressing a few last things. So we said that the tensor product of two R modules, M and N, is going to have the property that R linear maps or R module homomorphisms from the tensor product to an R module are going to correspond to bilinear maps from M cross N to that same R module. Well, it's very natural then to ask, what about taking tensor products of more than two modules? What is the corresponding thing going to be? And there is this generalization of bilinear, which motivates multilinear maps. So let's let M1 up through MK be R modules, and let's take a function from the direct product M1 cross M2 cross MK to some other R module M. That function is multilinear if it's R linear in each coordinate while we hold the other coordinates fixed. That means if you take M2, M3 up to little mk and you just fix those elements, and then you vary over all the possible inputs for the first coordinate, what are you getting? You're getting an R module homomorphism from M1 to M. And you have the same statement if you fix any subset of k minus 1 of these k coordinates. All right. So another thing that you might wonder about is we've seen that the set of R linear maps, R module homomorphisms between two R modules M and N actually has additional structure. Not only is it a set, but it's an abelian group and it's an R module. So it's this R module hom R Mn. You could ask the same thing about bilinear maps. Well, like, is there any structure to the set of bilinear maps from M cross N to some fixed R module P? And there is. So the set of these R bilinear maps from M cross N to P forms an R module in the same way that we saw before. So this is a BIL, like bilinear sub R Mn, and then here's a semicolon P to indicate that like you're taking the direct product of the first two things here, and then the codomain for all these maps is the R module P. All right, so it's not true that everything that we know about R module homomorphisms carries over to bilinear maps. So for example, if you have a bilinear map that goes from M cross N to some R module, M cross N is just a set. We're taking this direct product, this thing that is the domain here is just the set of pairs little m comma little n. And this isn't automatically an R module. So we remember, like, we can give the direct product the structure of an R module by having the ring act on the pair little m little n by taking R dot m comma n to be R dot m comma R dot m. That's not a natural thing to do from the perspective of bilinear maps. So we really want to emphasize that M cross N is a set. It's not an R module. We're not thinking of M cross N as an R module when we take a bilinear map. So if you take a bilinear map, you can take the kernel. You can take the set of all of the things that get mapped to the 0 elements of this R module P, but that's not going to be a submodule of M cross N. It's just a subset of this direct product set. So kernels don't have the same kind of natural interpretation. They don't play the same role when thinking about bilinear maps. Also, the image of a bilinear map need not be a submodule of P. What's going on is that if you fix some elements in N and you take all possible inputs in the first entry, you get an R module homomorphism from M to P. And the image of that homomorphism is a submodule of P. But if you pick a different element, you get a different R module homomorphism. So the image of that is also a submodule of P. So what you're getting is the union of a whole bunch of submodules that is not necessarily a submodule of P. So these are not super, super critical things that should be the first thing that you think about when trying to understand tensor products, but it is good to emphasize that Not everything that is true that we know about R module homomorphisms carries over in such a natural way to bilinear maps.